Today I'll talk about one important topics related to rank of matrix and matrix inverses. Okay, we know about that rank of matrix. We also discussed in previous class. Rank of some matrix equal to rank of related linear transformation. Okay, then we also discuss so many related theorem, and obviously this theorem shows that elementary row and column operations on a matrix are rank preserving. And then we also discuss the rank of a matrix is the dimension of the subspace generated by its column, and obviously we give some example related to that topics. Okay, today we discuss one important theorem. Okay, today we discuss an important theorem. Here, let A be an M cross N matrix. M cross N matrix of rank R. Okay, of rank R. Then what happened? Then R less than equal to M and R less than equal to N. Okay. Now, and and by means of a by means of a finite number of elementary elementary row and column operation row and column operations. Okay, a can be transformed a can be a can be transformed a can be transformed into the matrix what d equal to ir 0 1 0 2 0 3. Okay, where 0 1 0 2 and 0 3 are the zero matrices. Okay, and thus dii equal to 1. Okay, for I less than equal to r, and dij equal to 0. Okay, otherwise. Then we're also going to proof of this theorem. This one is an important theorem related to rank of matrix. Okay, let A be an M cross N matrix of rank R. Then obviously this rank less than equal to number of row and number of columns, and obviously by means of a finite number of elementary row and column operations, A can be transformed into the matrix D IR O1 O2 O3 here. Okay, sorry, here O3, and where 1 or 2 or 3 are 0 matrices, and dii equal to 1 for I less than equal to r, and dij equal to 0 for otherwise. Okay, so we also going to proof of that. This one is an important theorem. We are going to prove of that. Okay, so we start from that. If we write here proof, and if A is the zero matrix, then what happen? If A is the zero matrix, then R equal to 0. Okay, not a problem at all. And then the conclusion follows that D equal to 1. Then the conclusion, okay, conclusion follows that what t equal to a. Understood? And now suppose a not equal to 0. Okay, now suppose that a not equal to 0. Okay, then what happened? And r equal to rank of a. Okay, r equal to rank of a, then r greater than 0. Then what happened? Then r greater than 0. Okay, and the proof is by mathematical induction on aim. Okay, then the proof is the proof is by mathematical induction. Okay, the proof is by mathematical induction. Okay, on aim. Our aim is what? Aim is the number of rows. Okay, so now we erase our portion and going to further discussion of that. Okay, mathematical induction on aim. Okay, on aim, the number of rows of a. Okay, so now we're going to be discussing that suppose that aim equal to 1. Suppose that aim equal to 1, then what happen? Then by means of at most one type okay, by means of at most one type 1 column operation. Okay, operation and at most one type 2 and at most one type 2 column operation. Okay, A can be transformed into a matrix. A can be transformed into a matrix. Okay, A can be transformed into a matrix with a1 in the 1 position. Okay, in the 1 position. Okay, then by means of at most n minus 1, by means of at most n minus 1. Okay, type 3 column operation. Type 3 column operation. Okay, at most n minus 1 type 3 column operation. What happened? Okay, the matrix can be turned. The matrix can in turn be transformed into the matrix column operation. The matrix can in turn be transformed into the matrix. In turn be transformed into the matrix. Be transformed into the matrix Okay, here 1 0 0 dot 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 0. Okay, then what happened? Then obviously we note that what, there is one linearly independent column. There is one linearly independent, okay, independent column in D. Okay, so rank of A equal to rank of D equal to 1. Understood? Then what happened? That means the theorem is established for, the theorem is established for m equal to 1. Understood? Not a problem at all. Now we erase that portion and going to further discussion of that. That means what operations we used here? Just type 1 1 and 1 type 2 column operation, then 1, that means with 1 in 1 position, and then by at most n minus 1 type 3 column operation, then we get this matrix. Then obviously we show that this one is number 1 linearly independent column in D, then rank of A equal to 1. So we erase that portion and going to further discussion of that. Okay, so we write it here. That means we must prove, next we assume that okay, the theorem holds for, the theorem holds for any matrix, okay, with any matrix with at most m minus 1 rows, with at most m minus 1 rows, okay, for m greater than 1. Understood? Then we must prove that, okay, the theorem holds for, any matrix with m rows, okay. Then what happened? Then we also going to discussion about that. Suppose that A is any m cross n matrix, okay. Then what happened? If n equal to 1, then what happened? Then the theorem, that means, is established for m equal to 1. Then obviously, that means for m equal to 1, the theorem established, okay. And now we suppose that what? Suppose that n greater than 1, okay. Then what happened? Since a not equal to 0, okay, and aij not equal to 0 for some ij, okay, then by means of at most 1, elementary row and at most one, and at most one elementary column operation, we can move the non-zero entry, we each of type 1. Okay, we write it here, each of type 1, we can move the non-zero entry, we can move the non-zero entry. Okay, we can move the non-zero entry to the 1 1 position. Understood? That means first we then use type 1 column or row operation, then obviously we that means get 1 1 positions, that means some non-zero entry. Okay, then again we use by means of at most n minus 1 of at most one additional type 2 okay operation, type 2 operation, which shows that what at most one additional type 2 operation, we can assure a 1 in 1 1 position, we can assure a 1 in 1 1 position. We erase our portion and going to further discussion of that. Okay, then we can assure additional that means two type 2 operations. Okay, we can assure 1 in 1 1 position. Okay, assure a 1 in 1 1 position. Okay, then what happened? Then obviously by means of again by means of m minus 1 row operation. Okay, at most m minus 1 at most, by means of at most m minus 1 type 3. Okay, at m minus 1 type 3 row operation and at most n minus 1 type 3 column operation. Okay, what we get? We can eliminate all non-zero entries, we can eliminate one non-zero entry, we can eliminate all non-zero entry from all non-zero entry. Okay, and in the first row all non-zero entries in the first row and first column okay, so we also that means with exception 1 in the 1 1 entry. Okay, so or 1 in the 1 1 position. Okay, this that means this without this one all are in one first row and first column are become 0. Okay, we that means do some operations, then we find this one, then what we obtain. Okay, thus we write it here. Thus, with a finite number of elements, with a finite number of elementary operation, okay, a can be transformed, okay, into a matrix, what, into a matrix B, where 1 here 0 dot 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 0 and 0 dot 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 0, okay, and here B dash, okay, where B dash be an m minus 1 cross n minus 1 matrix, okay. Then what happened? Then we erase our portion and going to further discussion of that, okay. We also obtain this one, then now we erase our portion and going to further discussion of that. Understood? Then we also write here, then b dash has rank 1 less than b dash has rank 1 less than b, okay. Then what happened? Since rank of a equal to rank of b equal to r, since rank of a equal to rank of b equal to r, okay, and rank of b dash equal to r minus 1, okay. Then what happened? Then therefore r minus 1 less than equal to m minus 1 and r minus 1 less than equal to n minus 1 by assumption, okay, by induction hypothesis, okay, hypothesis. Understood? Then what happened? Then obviously we get, hence what we get r less than equal to m and r less than equal to n, okay. So we also do that, hence we write also by the induction hypothesis, okay, hypothesis b dash can be transformed by a finite number of okay, elementary row and column operation and column operation okay, into the m minus 1 cross n minus 1 matrix d dash, okay. That means by induction hypothesis b dash can be transformed by a finite number of elementary row and column operation into this one m minus 1 and n minus 1 matrix d dash, such that what, such that d dash equal to what? Here I r minus 1 and here O4, O5, O6. Okay, here where O3, O4, O4, O5, O6 are zero matrices. Okay, zero matrices. Understood? Then what we obtain, we erase that portion and going to further discussion of that. Okay, we obtain what? We obtain in this way, that is d dash consists of all zeros, d dash consists of all zeros. Okay, except for its first r minus 1 diagonals. Okay, r minus 1 diagonals or diagonal entries. Okay, then what happened? Which are ones? Understood? Then what happened? Then obviously let d equal to what? D equal to in this way 1 0 dot 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 0 0 dot 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 0 and here d dash. Okay, and then what we obtain? We obtain that we see that the theorem now follows. Okay, that d can be obtained from b okay, by means of a finite number of elementary row and column operation. Elementary row and column operation. Okay, column operations. Understood? Then what happened? Then thus, since a can be transformed, into b, okay, and b can be transformed into d, and b can be transformed into d. Okay, each by finite number of elementary operation, each by a finite number of elementary operation, a finite number of elementary operation. Okay, each by a finite number of elementary operation, a finite number of elementary operation. Okay, a finite number of elementary operation, we get what? A can be transformed into b and b can be transformed into d, and each by a finite number of elementary operation, e can be transformed into d. Okay, so each by a finite number of elementary operation, e can be transformed into d. Okay, then what happened? Then obviously, okay, sorry, a can be transformed into d by finite number of elementary operation by a finite number of elementary operation. Okay, so what happened? So we also write here finally d dash contains what? Finally d dash contains ones as its first or minus one. Finally, since d dash contains okay ones as its first or minus one, as its first or minus one diagonal entries. Okay, diagonal entries. Okay, and D contains ones as its first are diagonal entries and zero elsewhere. As its first are diagonal entries and zero elsewhere. Okay, and zero elsewhere. Okay, so we also established this theorem. Okay, this theorem we established now, and what we obtain this d. Okay, for uh, first r and r diagonal entries is 1 and other ones are 0. Okay, so we obtain this d and we also prove this theorem. If you get this type of videos, please subscribe my channel, and if you give like, click on like options. If you have any comments, suggestions, questions, write it in comment box. So today I stop here. Thank you.